Welcome to the next class of solid state devices. In this class, we will discuss Fermi level, intrinsic and extrinsic semiconductor material. Topic we will cover today is energy band diagram of metal, semiconductor and insulator. We will differentiate metal, semiconductor and insulator by the value of energy gap between conduction band and valence band. Then we will discuss fermi-dirac distribution function. From there, what is Fermi level, what is intrinsic semiconductor, what is extrinsic semiconductor, and extrinsic semiconductor can be of two types, p type and n type. We will differentiate that thing that will be covered today. Here you can see the energy band diagram for metal, semiconductor and insulator. For metal, conduction band and valence band get overlapped. So value of energy gap Eg, which difference between conduction band minima to valence band maxima, is negative here as it is getting overlapped. So you can have a conducting electron very easily as there is no energy gap between the conduction band and valence band. In case of semiconductor, this Eg value can be in order of 1 electron volt roughly. So if you apply some external excitation by any means, it can be in forms of current, in forms of temperature, magnetic field, electric field in some cases, then it will conduct. So semiconductor is having conditional conductivity, and if it is a insulator, then this energy gap value is in order of 3 electron volt, which is very high. If you apply some external excitation there, then to provide that much energy externally to the electron lies in the valence band, to move it to the conduction band, it is very hardly possible. Conduction only possible when if you provide some external excitation to the valence band, then some electron sitting in the valence band will jump to that conduction band energy level, then and only then it can carries current and conduction is possible. So metal having high conductivity, semiconductor is having conditional conductivity as energy gap value is very less. So you have to apply some external excitation there, then it will conduct. And if it is a insulator, then for insulator, it will not conduct anyhow, because this energy gap value is high, very high, and it is not possible, and no physical system available to provide that much energy. It is not in order of 3 electron volt, it is even more. So no physical environment and no physical device is possible to provide that much energy so that any electron from valence band can move to conduction band in the case of insulator material. As I said, semiconductor material is having energy gap value is in order of 1 electron volt. This is not true actually. This is some roughly estimated value. It can be anything. I have taken some very frequently used semiconductor material here and their corresponding energy gap values. Lead selenide is having 0.27 electron volt energy gap value. Lead telluride having 0.32 electron volt. Indium arsenide is a very famous semiconductor material having 0.36 electron volt. Lead sulfide 0.37. Germanium 0.67. Actually germanium, as you can see from your book, germanium having some energy gap value is 0.785, but these values are at 0 Kelvin temperature. So this value is of room temperature, means 300 Kelvin. So again for gallium arsenide, gallium antimonide, it is 0.726 electron volt. For silicon, it is 1.12 electron volt, 1.21 for 0 Kelvin, and 1.12 for room temperature. actually the formula is Eg is equal to 1.21 minus um, 2.23 into 10 to the power minus 4 times of temperature, absolute temperature T. So if you put T is equal to 300 Kelvin, then you will have this value for room temperature 300 Kelvin or 27 degrees Celsius, considered as room temperature for our country. Then indium phosphide 1.35 electron volt, gallium arsenide 1.44 on electron volt, then cadmium telluride, it is 1.5, cadmium selenide, it is 1.74, aluminium arsenide, it is on 2.12 electron volt, gallium phosphide, GAF, very famous semiconductor material. I'll tell you why this is very famous by this course. It is 2.24 electron volt. Then cadmium sulfide, it is 2.42 electron volt. Then gallium nitride, it is again a very famous semiconductor material, high wide bandgap semiconductor material. It is 3.4 electron volt. Then we have zinc sulfide semiconductor material is also available in two different types of crystal structure. One is cubic zinc sulfide, it is 3.54 electron volt. Then hexagonal zinc sulfide, it is 3.9 on electron volt. Then aluminium nitride, it is a very huge energy gap of 6.0 on 5 electron volt. This having this high value of energy gap is not at all a disadvantage always for a semiconductor material, because these are the high power semiconductor devices. You can fabricate high power semiconductor devices by using this wide energy gap semiconductor material or even ultra wideband semiconductor material. And nowadays these are very important semiconductor material for research. Silicon and germanium, as you know, it is indirect bandgap semiconductor. I'll say what is indirect and what is direct bandgap semiconductor later on by this course. But before that, for your convenience, silicon and germanium are indirect bandgap semiconductor, and all these compound semiconductor are direct bandgap semiconductor, except this gap, gallium phosphide. Okay. So, what is fermi-dirac distribution function? Fermi-Dirac distribution function describes the probability of finding electron at energy state of E. As we know, when electron moves around nucleus, it is having some energy band. That means within that energy band, it may have any energy value specified for this orbit. Fine. So let's consider we have some energy band of energy band, and in this energy band is having some particular energy value. So if we consider this E energy value, then what is the probability of finding of an electron there at the energy value of E? Conversely, I can say what is the probability that the E energy state is being occupied. That means occupation probability of the energy state E is called f of E. This is called Fermi-Dirac distribution function. It is not at all a function of energy, but it is a function of temperature only. So f of is the probability of finding electron at the energy state of E, and EF is called Fermi level of energy, some particular level of energy. As a conduction band and valence band, we know this is some virtual band, energy band of any material. EF is also some specified level of energy for material, and we don't know, still we don't know where it should lie exactly, but we will try to evaluate that. So if we plot this energy value E minus EF along this x-axis, and if we plot this Fermi-Dirac distribution function along y-axis, we will have a curve like this. And for different temperature, different absolute temperature value, for temperature T is equal to 0, we will have this rectangular shape. For T is equal to 300 Kelvin, but that means at room temperature we will have some kind of shape like this, or different for higher temperature. Now, if we consider some special cases of this fermi-dirac distribution function, certainly we will get some idea to evaluate where that Fermi level E of f should exactly lie. So let's consider the case when T is equal to 0 means absolute temperature is 0 and E is greater than EF. Look, consider this case from here. T is equal to 0 and E is greater than EF. So when E is greater than EF means this uh, numerator here it is positive, and T is equal to 0 means some positive quantity upon 0 means exponential infinity. So exponential infinity is infinity, and 1 plus infinity is also infinity, and 1 upon infinity is 0. So f of e is equal to 0. That means what? When f of e is equal to 0 means probability of finding any electron at energy state E is 0. That means there is no electron. So when absolute temperature is 0, there is no electron available above Fermi level. So we have considered some haphazard level, uh, energy level of E, which is above Fermi level. Under this consideration, now probability of finding any electron there is 0. So when absolute temperature is 0, it is impossible to find an electron above Fermi level, hence no conduction possible. Okay, why no conduction possible? We'll illustrate that thing. Before that, let's consider this case number 2 here. For absolute temperature 0, E is less than EF, is less than EF. Look here, when E is less than EF, that means E minus EF is negative quantity, absolute temperature is 0, so this denominator is 0, and E is less than EF means this is negative quantity, so exponential negative something means 1 upon exponential something. So 1 upon exponential, if you put T is equal to 0, that means 1 upon exponential some positive quantity upon 0, that means exponential 1 upon exponential infinity is 0, and 1 plus 0 is 0, and 1 upon 1 is 1. So f of e is 1. So it is obvious that at t is equal to 0, all the electron of the material lies below Fermi level, hence no conduction possible. That means when absolute temperature is 0 and E is less than EF, E is less than EF means I am considering some energy level which is below Fermi level. EF is the Fermi level, so E is below Fermi level here, and that is a shear event. That means it is obvious that when absolute temperature is 0, when absolute temperature is 0, all the electron lie below Fermi level. So if we consider some Fermi level, this two case is supporting the same thing. Thing is, if absolute temperature is 0, all the energy level which is occupied by electron will be below Fermi level. Now consider this special case 3 here, special case 3 here. Okay, when temperature is greater than 0 and E is equal to EF, E is equal to EF, then what will be the value of f of E? When E is equal to EF means this term is 0. So exponential 0 means 1. So 1 plus 1 is 2. 1 upon 2 is half. So it is 0.5. That means if your energy state which you have considered is on the Fermi level, it is equally probable that that electron may go to conduction band or may go to valence band. That means from there we can uh, gauge at least the Fermi level should lie exactly middle position between valence band maxima to conduction band minima. So if we consider Fermi level in the middle position of energy gap, that means at the value of Eg by 2, uh, that means exactly in between valence band and conduction band, then uh, what this two case 1 and case 2 is saying, that if you have any electron in valence band, that means below Fermi level allowed state is only valence band, there is no allowed state, and above Fermi level allowed state is only conduction band. So if you have temperature, absolute temperature 0, then all electron will lie in the valence band, hence no conduction possible. This point 2 is also supporting the same thing. If temperature is 0, all electron will lie inside valence band. Okay, and this condition 3 is saying that Fermi level should be and supposed to be exactly middle position between conduction band minima to valence band maximum. Another conclusion I can make it from here, if absolute temperature is 0, all the electron should lie in valence band. That means there is no electron available above Fermi level. That means all electrons should lie inside valence band. So no material is going to conduct. So safely I can say, if absolute temperature is 0, whether it is semiconductor, insulator, or even metal, nothing going to conduct. Conversely, I can say, if absolute temperature is 0, everything in this world behave like insulator. So what is Fermi level? Fermi level is a total energy level of electron, including kinetic energy and potential energy. If electron is having that level, it is equally probable to go to the valence band and conduction band. And difference between Fermi energy and Fermi level is the Fermi energy is only defined at the absolute 0 temperature, where the Fermi level is defined at any temperature. So for any temperature, every material supposed to have this Fermi level. This is nothing but some hypothetical level lies in between conduction band and valence band. Roughly we are considering that this Fermi level is exactly in between valence band and conduction band, just like EF is EC minus EB upon 2, that means EG upon 2 is the energy level of Fermi level. That thing is possible when electron and hole having equal effective mass. So you don't know what is effective mass. For your convenience, we know that electron having mass of 9.1 into 10 to the power minus 31 kg. So what is effective mass? So how do we measure that mass? This is not a electron. Any electron is not a separate body, so we can't measure this mass in some kind of weight machine like potatoes. So thing is, uh, any electron always should be inside some atoms, and these atoms is having some binding energy. Now when we have applied some external force there, we have measurement of that force. Now electron get accelerated, so we will have electron acceleration, and from the formula F is equal to m into a, mass into acceleration, we can calculate that mass. But thing is, this force which get applied exactly on the electron is not actually force we have applied from outside. There is some internal force as well on that electron due to the crystal structure and atomic bound. So if we adjust this internal force, and if we consider this external force only, and consider the acceleration is due to the external force only, by neglecting that internal force and adjusting the internal force in with the mass of electron or holes even, that is called effective mass. That means effective mass is also mass of electron or hole by adjusting the internal force there. So that is effective mass. So effective mass of electron and hole, if it is same, then and only then EF will lie exactly at the middle position of valence band and conduction band. Otherwise, the position is EF is equal to EC minus EB by 2, that means EG by 2 plus 3 by 4 KT natural logarithm of m star h, means effective mass of hole divided by effective mass of electron. If both effective mass is same, then this will yields a value of 1. So natural logarithm of 1 is 0, then this term will get vanished. You will have only this. So, so far we have discussed about Fermi level, and from this fermi-dirac distribution function, is a very famous function in the name of Enrico Fermi and Dirac P. So, we discussed that Fermi level or should lie exactly in the middle position of valence band and conduction band. Uh, if it is intrinsic semiconductor, firstly, and if it is intrinsic semiconductor and electron and hole is having equal effective mass, if it is not equal, then this Fermi level will slightly get shifted upward, that means towards conduction band, um, slightly due to this value for intrinsic semiconductor. But if it is extrinsic semiconductor, now this Fermi level is basically the level of electron energy. All this energy band or this energy values plotted here, these are the electron energy measure. So here, if it is a p-type semiconductor, as you know, p-type semiconductor means some silicon or germanium, and you are adding some trivalent impurity there, like aluminium. So silicon is having 4 electron, 4 valence electron, aluminium is having 3. So this 4 4 valence electron of silicon will form the covalent bond with 3 number of valence electron with this aluminium, and another extra valence electron of silicon will also find some covalent bond with some absence of electron, valence electron from this aluminium dopant, but this absence of a valence electron is called a holes. In case of n-type semiconductor material, you will have pentavalent impurities like arsenic. So all these 4 valence electron will go for some kind of covalent bonding with the 4 valence electron of arsenic on extra electron, on extra valence electron from arsenic will be there, and it will have some kind of crystal mismatch. So all these electron and holes, what we are having by adding some kind of impurity, some kind of foreign material there, this is nothing but crystal mismatch. So p-type semiconductor and n-type semiconductor, whatever it is electrically neutral. That whatever we have added is a atoms, impurity atoms, not impurity ions, and that is electrically neutral quantity. And p-type and n-type and you know, pure silicon or pure germanium is also a neutral quantity. So whatever it is, p-type or n-type semiconductor, it is electrically neutral. And as you adding some extra holes here, so electron energy gets sufficiently diminished. So this Fermi level will get shifted towards p, towards valence band. And for n-type semiconductor, you are increasing the number of electron, that means electrons are the majority carrier here. So this Fermi level will get shifted upward, that means towards conduction band, maintaining some distance with conduction band minima. Will have this distance, mathematically will calculate that. For p-type semiconductors also, this Fermi level is maintaining some fixed distance with this valence band maxima. Again, we will calculate that distance mathematically. Okay, let have a look some mathematics here. Okay, uh, we have had some knowledge about fermi-dirac distribution function, which is f of e is equal to 1 plus 1 upon 1 plus exponential e minus ef upon kt. Now let's consider two parameter here. One is n of e, which is the number of electron in the e energy state. Suppose we have considered some energy state e. Now, what is the number of electron available there in the energy state E? Now, what is G of E? G of E is the total number of available state, or this is called density of state, is defined as the number of electrons in energy state available between E and E plus del E. Here, G is the density of state, is defined as number of energy state available between E to D, E plus D. So that means what? Within that energy range, G is the total available state and N of E is the state occupied among this available state. So what is probability? By definition, f of E is the probability. So probability is number of occupied state divided by total state. This is also a probability here. And this is Fermi-Dirac distribution function as well. So can we write this f of E is equal to N upon G? So that means this is also equal to the Fermi-Dirac distribution function value. So N of E is equal to Gc of E, f of E. This is equation number 1. Why I have written Gc of E here? This is the equation for conduction band. So Gc of E is basically the density of state of conduction band, and f of E is the Fermi-Dirac distribution function. Ne is the number of electron occupied the E energy state, that means some energy range between E to D is N of E for conduction band. Now the same thing is for valence band, is P of E. P of E is the numbers of hole occupied the energy state between E to D is P of E. Gv of E is the density of state of valence band, and 1 minus Fe. If uh, your conduction band is occupation probability of conduction band is F of E, then occupation probability of valence band should be 1 minus F of E, because some electron will move from valence band to conduction band, then only conduction is possible. So when one electron will move valence band to conduction band, leaving on hole in valence band. So finding probability of any hole is basically the complement of the probability of finding electron in conduction band. So it is 1 minus Fe. If Fe is the finding probability in valence band, so 1 minus Fe is the finding probability of holes in valence band. So total probability is 1, because 1 minus Fe plus Fe is 1. This is equation number 2. Now, if we consider N0 is the total number of electron in the conduction band, so this Ne was the electron available between the energy state E to E plus D. Now, what is total? If we integrate that thing, this value of Ne throughout the entire conduction band range, that means from conduction band minima, which is EC, up to infinity. So it is N0 is equal to EC to infinity N of E d. So if you put the value of N of E here from equation number 1, you will have this equation. Now, density of state having some formula. We have considered Gc of E for conduction band and Gv of E for valence band. But this density of state Ge actually given by some formula here. In my next class, we will derive this formula again for density of state. So then that thing will be clear why density of state is like that. Before that, you just you can remember this. We'll go for necessary explanation in next class for that. So G of E is equal to 4 pi into 2m star is the effective mass. If it is for electron, then m e star, for whole say m h star. So m star generic expression power 3 by 2 upon h square. H is the Planck's HQ. H is the Planck's constant multiplied by root over of energy. For conduction band, I'm just modifying this formula here. I'm rewriting this formula for conduction band. It is Gc of E is the density of state for conduction band is 4 pi to mc star. Mc, I have considered here the effective mass of uh, electron in conduction band. So it is mc star power 3 by 2 upon hq root over of E minus EC. I have considered some energy, haphazard energy state E. E minus EC means somewhere supposed to be inside conduction band. So EC is the conduction band minima. So E minus EC is the energy here. And for valence band, if we rewrite this generic formula, for conduction band, Gv of E is equal to 4 pi to mv star. Mv star is the effective mass of hole in valence band, power 3 by 2 upon h cube root over of ev minus e. Here ec, e minus ec, here ev minus e means inside valence band. Ev is the valence band maxima, so ev minus e means somewhere inside valence band. Now, if we try to evaluate this integral in 0, means total electron available in conduction band is nothing but integration over EC to infinity GC of E FE dE. So we have all the values. This is the value of GC of E. So we'll put here, and we know the value of fermi-dirac distribution function. So we'll put the values. Before that, we will go for some kind of necessary approximation. Let's consider this E minus EF is more than KT. E minus EF is more than KT. Means what? Something, some huge quantity at the numerator of this exponent. So that means exponential something more means huge. Exponential something more means huge. So 1 plus some huge quantity is nothing but we can neglect 1 in that respect, because if you add 1 with 10,000, I think that is um, not very higher value than 10,000. If you add 1 with 1, then this is effective. But if you add 1 with 10,000 or 1 lakh, then if you can neglect this one, then I think that will not having much more effect. So under this consideration, we can write it is 1 upon 1 plus exponential something means 1 upon exponential something by neglecting this 1 here, and that means 1 upon exponential something means exponential negative something. So this approximation is basically called Maxwell-Boltzmann approximation, under the consideration that E minus EF is more than KT, at least 3 KT. If you consider that probably this picture is known to us previously, this is along this x-axis it is E minus EF, along y-axis this is energy. Under this Maxwell-Boltzmann consideration, we will have this type of curve here. If you consider actual rectangular curve, it will differ not more than 5% of area values. So we can consider this if E minus EF is much more than 3 KT or KT even, then safely we can approximate by this Maxwell-Boltzmann approximation. Now, what about this N0? If we try to evaluate this by putting the value of GC of E and this Maxwell-Boltzmann approximated value of fermi-Dirac distribution function, then we will have this equation. Now if we replace E minus EC upon KT is equal to eta, so D is equal to KT d eta. So if we want to change the limit here, so when E tends to EC, then eta tends to 0, and E tends to infinity, eta tends to infinity. So N0 is nothing but integration 0 to infinity 4 pi to MC star upon power 3 by 2 divided by HQ root over of eta KT into exponential of this minus of E minus EF. So I have used some trick here. I just use some extra EC. So I have used some minus EC here, minus EF as here, and again plus EC. That means this EC will get cancelled out. Then it will remain like same, but I have taken in that way to put this value here. Okay, things will be clear. Look here, it is integration 0 to infinity 4 pi upon h cube into 2 mc star kt power 3 by 2. I have taken this kt inside. This is 1 kt and this is root kt, means kt power 1 plus half. So kt power 3 by 2 again. I have taken kt inside, leaving this root eta here. Then I have decomposed this exponential term. This first term is exponential minus e minus ec. I have taken here, and again another thing we have exponential minus ec minus ef. I have taken upon kt d eta. No problem with that. Look here, this e minus ec upon kt is here. So this is nothing but eta. To do that, I just introduce on EC here, on plus and on minus EC here. So if you rewrite this equation, you will have this thing here. Eta is the parameter, d eta here. So eta is the parameter. So all this term, this 4 pi to mc star kt upon 3 power 3 by 2 divided by hq, and exponential all this quantity ec minus ef upon kt. So these are constant. So whatever we have inside this integration is integration 0 to infinity eta power half exponential minus eta d eta. Now if we evaluate this integral, I should suggest please have a bit study on gamma function. You may have Google search. You will have a 6 or 7 formula there. Please be conversant with the necessary derivations of this formula. At least you remember that. If it is not covered in mathematics syllabus yet, then please have a study on that. So this this equation basically means 0 to infinity eta power half exponential of minus eta d eta is means exponent x to the power half exponential of x exponential of minus x dx is nothing but gamma 3 by 2, and gamma 3 by 2 means half gamma half, and gamma half means root pi. So half gamma half means root pi by 2. If you know formula, then there will be no problem to understand this. If you don't know, please have Google search. You can find that thing there, this equations, this formula of gamma function there. So from there, if you replace this integration value to this equation, then we will have this type of value of N0. What is N0? Total number of electron in conduction band is 2 times of 2 pi mc star kt upon h square, this whole power 3 by 2 into exponential of minus ec minus ef upon kt. This is nothing but N0 is equal to Nc. Nc is the effective density of state of conduction band into exponential minus Ec minus Ef upon Kt. This is a very, very important equation. You always need that equation to solve mathematical problem in solid state devices, and you have to remember all these necessary derivations and this formula throughout the journey of your career. And again, what is the value of NC? As we replace here, it is 2 into 2 pi MC star KT upon H square power 3 by 2, the value of effective density of state of conduction band. If we do the same for valence band, the total number of hole available in valence band, it is integration over GV of E. GV of E is the effective density of density of state of valence band into 1 minus Fe. This was our equation, into D. So 1 minus Fe means exponential of 1 plus exponential EF minus E now. E minus, not E minus EF, EF minus E upon KT. You can check it out why I have written in that way. And if you go for Maxwell-Boltzmann approximation, here we'll have exponential minus EF minus E upon KT. Now, if we replace the value of 1 minus Fe and density of state of valence band, we will have this type of formula. And from there, if you replace Ev minus E upon KT by eta and solve as we have done previously, if you solve accordingly, then you will have P0 P is equal to NV exponential minus EF minus EV upon KT. This is again the total number of hole in valence band, very important formula. Whereas effective density of state of valence band is 2 times of 2 pi m p star or mh star, that is that is effective mass of hole in valence band times of KT divided by H square whole power 3 by 2. So this number of electron available in conduction band and effective density of state of conduction band, number of hole available in valence band, then effective density of states of valence band is a very, very important formula. You have to remember always, and you have to know the process of derivation. Now, if we want to describe intrinsic semiconductor, what is intrinsic semiconductor? It is pure form of semiconductor, and as we know from our knowledge of Fermi level from today's class, this Fermi level should lie in between valence band and conduction band at exactly middle position, not exactly, under some condition, exactly middle position of conduction band minima to valence band maxima. And just we derive N0 is equal to NC exponential EC minus EFI upon KT. I have written EFI for intrinsic semiconductor. That means this is the Fermi level of intrinsic semiconductor. Now, what is the number of hole in valence band? P0 is equal to NV exponential EFI minus EV upon KT. I just replace this EF by EFI for intrinsic semiconductor. Now, according to mass action law, what is mass action law? If number of electron is say N0, number of hole is P0, then Ni is the intrinsic carrier concentration. So N0 into P0 is basically square of Ni. That means Ni square. So if you we know the value of N0, we know the value of P0. So P0 into N0 is Ni square. So if we multiply the value of N0 into P0, this is nothing but NC NV exponential of minus EC minus EFI upon KT into exponential minus EFI minus EV upon KT. This will give you the value NC NV exponential minus EC minus EFI plus EFI minus EV upon KT. So this plus minus EFI will get cancelled out. You left with NC/NV exponential minus EC minus EV upon KT. So what is the value of Ni square? This is NC/NV exponential minus Eg by KT, because you know EC is the conduction band minima, EV is the valence band maxima. This difference we know is the energy gap Eg. So what is the value of Ni? This is root over of NC/NV exponential of minus Eg upon 2 kT because of this root. So 2 kT. Now what is n-type semiconductor? So for n-type semiconductor, you have this as majority carrier concentration is electron concentration. So electron concentration is Nc exponential of minus Ec minus Ef upon Kt as we derived. Now what about this N0 upon Nc? If you divide it by Nc, so you will have this equation. Now what is this N0 upon okay, now let me rewrite this equation again other ways. So if we take natural logarithm both side, then what we'll have, you can write one more extra line, exponential. So this means natural logarithm of N0 upon Nc. Natural logarithm of N0 upon Nc is negative of exponential negative of minus Ec minus Ef upon Kt. So if you multiply it by Kt, you will have this equation. Now for n-type semiconductor, what is N0? Majority carrier is exactly the number of donor impurities you have added from outside. So number of donor impurity is almost is the number of electron available, a number of majority charge. So this N0 is nothing but Nd. So if you replace that thing, so Ec minus Ef is equal to Kt natural logarithm of Nc upon Nd. Now Ef is Ec minus Kt natural logarithm of Nc minus Nd. Nc upon Nd means what? We have seen earlier that for n-type semiconductor, where should this Fermi level lie? It is near about conduction band minima and maintaining some fixed distance from conduction band. It is Kt ln Nc upon Nd. This distance we are discussing n-type semiconductor, so it gets shifted. This Fermi level will get shifted towards the conduction band minima. Now this distance from conduction band to Ef, this distance is Kt ln Nc upon Nd. If it is a p-type semiconductor, then what is the value of P0? We have derived, it is Nc exponential Nv exponential of minus Ef minus Ev upon Kt. So P0 upon Nv is this much. If we take natural logarithm again and if we rewrite this equation, we will have Ef is equal to Ev plus Kt natural logarithm of Na upon Nv. What is Na? P0 is Na because for p-type semiconductor, hole is the majority carrier, and hole means what? Whatever trivalent impurity you are adding means acceptor impurities. Trivalent impurity is called acceptor impurity, and pentavalent impurity is called donor impurity, because it is donating electron, and this trivalent impurity is accepting electron. This will be clear from here. For p-type semiconductor, this Fermi level shifted towards this valence band, maintaining some distance with this Ev, and this distance is, that means look from here, Ef is basically Ev plus some other value, and this value is Kt natural logarithm of Na upon Nv. So I think we have given enough mathematical explanation why the Fermi level should lie exactly at the middle position under certain condition, exactly at the middle position for intrinsic semiconductor, and why it gets shifted towards conduction band for n-type semiconductor, uh, and why it get shifted towards valence band for p-type semiconductor. We have physical explanation as well, because these are the major, this all this energy level are the measures of electron energy. For p-type semiconductor, we are adding um, holes there, and electrons are becoming minority carriers, so electron energy getting reduced. That's why the Fermi level is getting downward. And for p-type, for n-type semiconductor, we are adding electron by this pentavalent impurities, so electron energy getting increased, that is shifting the Fermi level towards upward. I think we should stop here. Other thing will be discussed in my next class.